Hello. Today, we'd like to present how you can quickly and smartly build a complete and consistent software architecture for an IT system using so-called composite consistency rules. We'll build the software architecture using a script in Sparx's Enterprise Architect tool. On the Google Drive, there's information about diagram types, their elements, and simple and composite consistency rules. We'll use the ecmdiref.xml script to process the consistency rules. We'll use only composite rules to show the construction of the software architecture for a sample IT system called Office from the context diagram, the most abstract UML diagram, to the most implementation-oriented UML diagram, the component diagram. First, we need to copy the script from the Google Drive page. We go to the browser, copy our shortcut, and go directly to the drive named Consistency Rules. There are files describing the consistency rules, as well as a set of patterns that we can import instead of manually creating a UML diagram. It would be useful to review these consistency rules before building the software architecture, so that we know on which diagrams they can be used in and the creation of which target diagram elements these rules enable. Next, we go to the JScript directory and download the ecmdiref.xml file containing our ecmda script for quickly building consistent and complete software architecture. The installed.txt file shows the place in Enterprise Architect where we can import this ecmda script. So, we download our script file to our local drive. Next, we open the Enterprise Architect tool. We should create a new local file and name this file simply Office. The first step after creating this model will be to create a package named Office, which will store all our models and diagrams describing the software architecture of our sample Office IT system. The next step will be to import our script from the Configure menu and the Transfer option. There we choose the option Import Data, select Import File, and select the appropriate file from the Downloads directory. Then select Automation Script and Import button below. The Import Complete window will appear, and we already have this script imported into the tool. Let's now create packages in which we will store our software architecture models and diagrams of the Office IT system. These packages are primarily the views defined by the ecmda solution. The first is the context view. Next, we create the business view, which will contain all the models and diagrams related to the business view of our architecture. We will name the next package after the third ecmda view, the system view. And the last view of our solution will be called deployment view. The ecmda script works as follows. It searches the current package for tags named consistency rules, and once it finds one, it reads and processes it, creating a package with a more implementation-oriented diagram. Therefore, we should first create a context diagram in the context view package. Simply enter the consistency rules tag and the values in the form of a consistency rule into our context view package. In our first script run, the script behaves slightly differently than in the following cases, as we will now simply import the context diagram from the internet. To import this diagram, we simply enter the Office pattern name instead of the composite consistency rule. We do this to avoid manually modeling the Office system context. We execute our script by selecting the empty context view package, pressing the right mouse button, and a pop-up menu will appear. First, select Specialize, then Scripts, and the available scripts will be displayed. Currently, the only script available is the ecmda script. This is the only instance where our script will run on an empty context view package. Attempting to run the script under any other circumstances will result in an error. After the script is processed, a context layer package will be created containing a context diagram of the Office system. The Office process allows the Office to process a client's request to deliver a decision to the client and also allows for the creation of a report based on the decisions made. This diagram shows on the left side information in the form of an event called request, which triggers the main process visible in the center of the diagram. These elements are compliant with the Erikson-Pinker notation. On the right side, the result of processing the Office process is shown as an object. This is an instance of the decision class and an instance of the report class. At the top of the diagram, you can see an object representing the rules by which the process works. And at the bottom of the diagram, an element storing the process data. It seems that the main process can be decomposed into two subprocesses. The first one related to the processing of the application, ending with the creation of the decision, and the second subprocess, the processing effect of which is the creation of a report with statistics of the decisions issued. Therefore, we need to set two composite consistency rules on the diagram, which will allow us to obtain a less abstract diagram decomposing the main process into these two subprocesses. The first composite rule placed on the request element is the one shown below. It states that based on the elements E, event named request, V, process named office, and I, instance of class decision of diagram X, the context diagram, the following elements should be created on the target diagram are the business process decomposition diagram. Input instance I of class request subprocess V named request subprocess, and output instance I of class decision. The second composite rule, in the form just displayed, states that based on the input element I with class decision, the process V named office, and the output element I with class report of the context diagram X, a subprocess V named report subprocess will be created with an input instance of the decision class and an output instance of the report class in the target business process decomposition diagram with the symbol R. Let's now run the script. Wait until the process complete message appears in the system output window and open the decomposition diagram. The decomposition diagram contains the two subprocesses we just discussed. The first subprocess will be created with an input object of class request and an output object of class decision. The second subprocess has an input object of class decision and an output object of class report. Before we set the rules on the next elements of the diagram, let's take a look at the target software architecture we'll get at the end of our example. First, we created the context diagram X with a single click. With the next click, we created the process decomposition diagram R. After another click, we'll get the business use case diagram B. Then, based on these two diagrams, with a single click, we'll create the business use case realization diagram, also known as the process diagram. From the business process diagram, with a single click, we'll create three more diagrams: a business class diagram C, a business state machine diagram S, and a system use case diagram U. Successive single clicks on the system use case diagram and the business state machine diagram allow us to create a system use case realization diagram, Z, also known as a front-end diagram. Another click creates an implementation use case diagram, Y. Another click creates an implementation use case realization diagram, also known as a sequence diagram with a symbol Q, or a backend diagram. And the final click allows us to create a component diagram. In other words, by using a context diagram and clicking 10 times, we can obtain a practically consistent and complete software architecture in one specific aspect. We will demonstrate this method of building software architecture later in the video. This resulting software architecture can be further refined to provide a detailed description of the software architecture of the entire IT system in every aspect. Returning to the process decomposition diagram, let's set a consistency rule on the input object of the request class, which will allow us to create a business use case diagram with the symbol B with actors client, employee, and manager, using the business use case named request services. The second composite consistency rule we'll place on the request subprocess is a rule that visualizes a business process composed of 5 activities connected by control flow and additionally connected by object flows with instances. So now let's run the script on our business process decomposition package. This will create 2 packages and 2 diagrams. A diagram of the request subprocess in the request subprocess package of the business process layer, the business view, and a business use case diagram with a business use case named request service and 3 actors, client, employee, and manager. In this business use case, we also introduce a complex consistency rule to create a business process scenario, but this time it allows us to associate process activities with partitions that represent actors. If we now look at the business process, we will notice that there are no partitions. There are only actions linked by control flow and actions additionally linked by object flow. If we now run our script on the package containing the business use case diagram, after executing the script, that is, after the process complete message appears in the system output window, we will see how this diagram has been modified by the second rule, visualizing the business process. Therefore, after this second script execution, the activities and objects remain unchanged, but they will be inserted into the individual partitions corresponding to the names of the business actors in the business use case diagram. On this employee partition, let's now set a composite consistency rule specifying that from the process diagram, with the symbol a diagram of system use cases will be created. Based on the activities contained in this partition, 2 system use cases will be created with the names of these activities. The next composite consistency rules we'll set here are a composite rule specifying that a business class diagram be created based on the classifiers of objects associated with a given activity. Here, we have objects of the decision class and objects of the request class. Therefore, these 2 classes should be created and linked with an association relationship. We also set another composite consistency rule, this time on the object, specifying that a business state machine diagram be created based on the states of objects of a given class in the business process, with states such as sent, register, or approved. Now let's run our script on the request subprocess business process package, and 3 diagrams should be created. The first diagram is in the logical layer, a business state machine diagram of the request object, a diagram of the request and decision business classes, and a diagram of the system use cases named after our module, request subprocess. The text process complete appears, so let's open the business class diagram. There are 2 classes there, request and decision. Let's remove the string tags from the diagram properties where these classes are located. These classes are located in the context layer package with the context diagram. If we want to move them to the business class package, we'll do it manually. The next diagram, created from the process diagram, is the business state machine diagram. This diagram consists of a single state machine named request, and this state machine contains the following elements: sent, registered, and approved, so all those states that we have shown in our business process diagram. We also set a composite consistency rule in the business state machine diagram to visualize the scenario in which the instances and their states will be described in the system use case realization diagram. Here, in the symbol parameter z of this diagram, we need to enter the scenario's destination. Therefore, we enter the module name request subprocess and, separated by a comma, the name of the system use case too. Registration. Of course, a third diagram was created from the business process diagram, the system use case diagram. In this diagram, we set up a composite consistency rule for the system use case, named 2, registration, which will enable us to visualize the system use case realization diagram scenario. Now, let's run the script first on the package containing the system use case diagram. Wait a moment longer. The process complete text is already displayed, so let's open the system use case realization diagram. Let's see what it looks like. There are only activities in 2 partitions, system and user. There are no objects. To enter the object flow, we now need to go to the package containing the business state machine diagram and execute the script with a composite rule stored in the state machine named request. After executing the script, the process complete text appears. Close this diagram and reopen it to see how it has changed after this second script run. We've now created instances with the appropriate states of the request class, as we've set a composite consistency rule on the machine state for the request object. The next rule we need to set is a parameterless rule, allowing us to create a system use case realization diagram. We set it on the system partition. It will create implementation use cases based on the action names in the system partition. Let's run the script on the package containing the system use case realization diagram, often called the front-end diagram because it represents the user's interaction with the system. This will allow us to obtain a diagram of implementation use cases in the internal layer. Let's see what our diagram looks like. It consists of 3 implementation use cases and 1 system use case from the previous diagram. hence the from request subprocess text underneath. In the first implementation use case, we introduce a scenario for the sequence diagram in the form of a composite consistency rule displayed on the screen. This sequence diagram will consist of 3 lifelines, each with the symbol L, and 2 messages, each with the symbol M. The message names and their parameters will be created based on the object flow to and from the action located on the system use case realization diagram, corresponding to this first implementation use case. Let's run the script on the current package. The sequence diagram shows us 3 lifelines. This shows that messages will be sent between our module and the database via an additional component called middleware. Note that this maps the object flow to and from the one. Form display action from the system use case realization diagram. The input flow of objects from an object of class request with state sent is mapped to a download message with parameters send of class request, and the output flow of objects to an object of class request with state filled is mapped to an update message with parameters filled of class request. Let's now see how these message flows will be mapped to interfaces in the component diagram. We do this by placing a composite consistency rule on the message flow between any components. Therefore, executing the script on this consistency rule has created a component diagram. The process is complete. Let's move the component diagram package to the appropriate location and disable the indication of the package names containing our components in the diagram. So we have 3 default components: request subprocess, middleware, and database linked by interfaces named download and update. And that would be the end of our example. Now we should detail the remaining aspects or use cases to fully present our entire software architecture. Let's take a look at how all the consistency rules were created in our software architecture and then demonstrate the application of composite pattern-driven consistency rules. That is, how we can import some UML diagrams from the internet by specifying only their names without manually designing them. When creating individual diagram elements, the script simultaneously creates links of the dependency type from the source element and with the consistency rule name used to create the target element. This can be seen by creating a custom UML diagram and pasting the contents of the individual diagrams into our custom diagram. To view composite consistency rules without the clutter of created dependency names, let's disable the connection names in the diagram. Now, our horrendous diagram has become more user-friendly, and we can see a little more clearly how the individual elements in each diagram were created. Let's now return to composite pattern-driven rules. We first created a context diagram from such a pattern. This pattern is simply a pre-prepared XML package, ready for import into Enterprise Architect. Importing a context diagram, as we saw at the very beginning, requires the context view package to be empty and the context view package to contain a tag named consistency rules and values with the name of this diagram. Importing diagrams with business processes is different. The only composite rules we can use to import our business process diagram are the displayed rule applied to the decomposition diagram and another displayed rule applied to the business use case diagram. In both rules, we specify the name of the pattern in decorative brackets. Let's say this pattern is Office Business Process. Let's move the existing business process to a different location and run the script on the decomposition process diagram. The first pattern-driven rule uses the input and output object from the subprocess in the process decomposition diagram to set the classifiers for these objects in the imported business process diagram after import. The script also sets the state of the first and last objects to the same state as the input and output objects in the business process decomposition diagram. The second rule, however, sets the names of the imported partitions to the same names as the actors in the business use case diagram. Therefore, executing these 2 rules should ensure that the pattern from the internet will fit into our just-designed software architecture. The imported patterns also have composite consistency rules set on certain key elements, eliminating the need to consider further development of the software architecture. Therefore, all partitions have composite consistency rules, enabling the creation of a diagram of all system use cases resulting from the activities described in the business process. Furthermore, One of the activities has a composite consistency rule, enabling the creation or update of a business class diagram. Composite consistency rules have also been set on selected objects to enable the creation of a state diagram on the business state machine diagram if such states are missing. After running the script on the imported business process diagram, our existing business class diagram remained unchanged. However, another state named decision with states from the imported business process appeared in the business state machine diagram. The system use case diagram also expanded to include all the system use cases resulting from the activities included in the business process. Therefore, our imported business process diagram fit well into the construction of our software architecture. Let's now enter a composite pattern-driven rule on the third system use case. 3. Approve. This rule is displayed on the screen. Within double decorative brackets, enter the value for the V parameter, request approval frontend. After running the ECMDA script, the system use case realization diagram, named request approval frontend, will be imported. You must manually rename the diagram to 3. Approve and delete the existing diagram as it is empty. After importing the diagram, the script sets the objects in the imported diagram to the classifiers of the input and output objects to and from the 3. Approve activity in the business process diagram. The script also assigns the states of the first and last objects, just as it assigns the states of the input and output objects to the 3. Approve activity from the business process diagram. Furthermore, the imported diagram already contains a composite consistency rule in a partition named system. Therefore, there's no need to consider further development of the software architecture. Simply run the script on this package to obtain further, more implementation-oriented diagrams. This way, our imported front-end diagram fits well into the development of the software architecture. To obtain a sequence diagram from the internet, simply enter a composite consistency rule with the name of the back-end diagram into the selected implementation use case. To import such a diagram, we enter the pattern name in triple decorative brackets in the V symbol parameters. In our case, this is request downloading backend. When you run the ECMDA script, the sequence diagram will be imported into a package named request downloading backend, which is also named 1. Form display in a package named 1. Form display, which is created in a package named 3. Approve, which is created in the request subprocess package of the sequence layer package of the deployment view package. The imported diagram already contains a composite consistency rule for the message to create the appropriate interfaces between components. Therefore, if you import a sequence diagram, further development of the software architecture shouldn't pose any additional obstacles. Simply run the script on this package to obtain another, more implementation-oriented diagram, the component diagram. This way, our imported backend diagram will fit seamlessly into the software architecture. The updated component diagram now includes new interfaces. Next, in the background, we'll present relationships representing composite consistency rules created between models imported from templates and current components. And that's the end of our video. Thank you very much for watching. Our software is in a prototype version, so there are likely some bugs. However, we're curious whether this type of software will shorten and optimize your work on IT systems. Therefore, we're asking for feedback on what could be improved and what could be enhanced. Perhaps it would be worthwhile to design business processes in BPMN rather than UML activity diagrams. Perhaps it would be worthwhile to enhance the diagrams related to presenting screens to users. Or perhaps it would be worthwhile to refine the test generation section for testers. But we're currently considering how to expand these patterns using existing business process patterns, front-end diagrams, and back-end diagrams to include the ability to generate software code in .NET, Java, or Angular. Currently, there aren't many such patterns, so we'd love to hear your suggestions and perhaps even make them available for everyone. Your suggestions and information will also determine whether this type of software is worth developing into a professional version, so that it doesn't just become a curiosity for analysts, designers, or architects. We look forward to hearing from you.